In quantum mechanics, we have operators, and these operators in general obey some commutation relations, for example, between the position operator, x, and momentum, p. Let's assume that we have just one dimension, so we have x and p. P is related to the derivative of x with respect to time, and this commutator we know from basic quantum mechanics that is equal to I h bar. But what about the path integral formalism? Can we see such commutation relations by using path integrals? Well, the answer is not so simple. For example, let's consider a free particle, so we will still consider a free particle and we want to find something like this commutation relation. But with path integrals we have something of the following kind. We have integral over this dx here. Dx, you have to interpret this as a product of infinitely many differentials, because we have a set of trajectories from one point to another. So basically here we have the starting point y0, which is equal to x evaluated at the time 0, and then here we have y1, which is equal to x evaluated at time capital T. And in between we have possible trajectories, because we are in quantum mechanics, so there is not a classical path that the particle is going to follow, but rather we have several amplitudes that we have to sum, and from that we are going to find the most likely trajectories in general. And so we are extending the laws of classical mechanics to quantum mechanics. We want to extend the principle of least action. So basically, if we take a generic trajectory, we are going to split up into an infinite amount of, let's say, parts, and the time that the particle takes to, for example, reach this point here from this point, so basically to travel this distance, is dt. This is the amount of time that it takes. And if you remember, we first assumed that this time dt was finite, so we have some small intervals dt, delta t, that basically will go to 0, and they will become differentials like this. So this dx here is going to consider, so this is going to be proportional to dx of t1, dx of t2, dot dot dot, dx of tn, and so on. So these differentials have to be interpreted like this. And then we have, of course, to integrate over all those differentials, because if you integrate over the different variables, we are going to get the other paths, right? So that's how we are going to consider this multitude of paths by integrating over all those possibilities. Then we have e to the I s of x, so the action will be a function of x, which is itself a function, remember that, divided by h bar, and in principle we have other functions inside the path integral. So for example, we can have x of t multiplied by momentum p of t, and if we subtract p of t x of t like this, well, you have to think that we are going to get a zero result, right? Because in this case, inside this path integral, these are going to be just scalars. So when you're summing these scalars, you're going to get a zero result. So what's the point? What's the matter? Why do we get something like this with the path integral formalism, and is there a way to extend it to include such commutation relations? The answer is yes. Incredibly, the answer is yes. We can still find commutation relations of this kind from the path integral formalism. One way to do that is to consider, for example, the following things. So instead of considering time t here, we put t minus, and instead of considering t here, we are going to put t plus, like this. So we think that we are considering the following intervals. So 0 is less than t minus, which is less than t, which is less than t plus, which is less than capital T. So we are considering this interval here, and here we are considering t minus, and here we are considering t plus. We will take the limit, of course, where t plus will go to t. So t plus will become closer and closer to t from the right, as you can see. And t minus will also be closer and closer, will also go closer and closer to t, so from the left in this case. And now we will see what we are going to get. And remember that in this case, I'm assuming that when we integrate over these path integrals, we are starting from this point, and then we are going to this point. So these 2 points, the 2 endpoints, are fixed. Just like in the classical case where we have an action and we are fixing the 2 endpoints of the trajectory. Now, we are considering, as I said, a free particle, so we have the action s of x that can be written in the following form. Integral of 1/2 the mass of the particle times x dot squared dt. Now, we are going to discretize our integral in the following way. So we have x of t times p of t minus, which is here. We are going to discretize it in the following way. So basically, instead of x of t, we are going to write x sub k. Then, of course, p of t minus will be m, that we can factor out, the mass. And then we have xk minus 1 divided by delta t. And then p of t plus times x of t will become m times x sub k times x sub k plus 1 minus x sub k divided by delta t. Now, the path integral, when you consider this discretization, will become like this. So we have the factor m, which is a simple factor that we can factor out. Then we have to integrate. Then this, the path integral that we have here will be proportional to what I'm going to write below. In the sense that, yes, the differential dx, this measure dx, will be proportional to the following product over j from 1 to n minus 1 dxj. So we are going to take the product of all these differentials. And then, since we are discretizing these quantities, we can also rewrite the exponential with the action. We can rewrite it like this: e to the I 1/2 m over h bar, and then we have xj plus 1 minus xj squared divided by delta t squared, and we also have to multiply by dt, delta t here, and we are going to put this inside the product. So like this. When we take the product of all these exponentials, we are going to get a sum inside the exponential, right? So we are going to get back our original action, if you think about it, right? Which in this case, when you discretize the integral, will simply be given by a discrete sum, like in here. Then you have to assume that when we let delta t go to 0, we are going to get back our previous expression. That's what we have to think. Then, remember that we also have x sub k, which multiplies x sub k minus x sub k minus 1 divided by delta t. And then we have minus x sub k plus 1 minus x sub k divided by delta t. Now, we are going to focus only on the integral over dxk. So basically, we are going to focus among all these integrals here. We are going to take, since they are products, we are going to focus on the integral over dxk. And remember that we have to integrate from minus infinity to plus infinity to account for all the possibilities. So we still have the factor m that we can include in here, so we can insert it in this integral. Then we have this that we are going to consider here. So we have xk multiplied by xk minus 1 divided by delta t minus x sub k plus 1 minus x sub k divided by delta t. And then among all these products, in here I'm just going to consider e to the I 1/2 m over h bar x sub k plus 1 sub k plus 1 minus x sub k squared divided by dt, delta t. So I'm simplifying this delta t with this delta t squared. And then I also need to consider another exponential, which is e to the I 1/2 m over h bar x sub k minus x sub k minus 1 squared divided by delta t, like this. And then, of course, outside of this integral here, you also have the other products of the other differentials with the exponentials. So you have the exponentials and the differentials, dx1, dx2, all the differentials except for dxk, because you can see that the differential over k, when j is equal to k, is also going to integrate over this part. So the integral over this part is only related to the integral over dxk, because all the other integrals can factor out. So you get a multiplication of all the integrals with such terms without this part that we are going to consider with the integral over dxk, of course. But this integral can be performed. And in particular, now we are going to rewrite it. And you can check quite easily, I mean, this is just simple calculus. You can write it as minus integral from minus infinity to plus infinity, dxk, xk, and then we have I h bar derivative with respect to xk of this. So I have e to the I 1/2 m over h bar x sub k plus 1 minus x sub k squared divided by delta t, e to the I 1/2 m over h bar x sub k minus x sub k minus 1 squared divided by delta t, like this. So you can check that when you consider the derivative of this expression, you're going to get back exactly this. So this is simple calculus. You simply have to take the derivative of these complex exponentials and you're going to get that. But now we can integrate by parts. So if we integrate by parts, considering that we are integrating from minus infinity to plus infinity over dxk, we are going to get the following. So we get plus, instead of a minus, we have I h bar. So, by the way, we are also going to neglect the boundary term. So you also get a boundary term from the integration by parts. And it is much simpler to motivate the fact that the boundary term vanishes if you don't consider this I, and for example, instead of I, you consider minus 1 instead of I, because in that case you will simply have two decaying exponentials that will go to 0. But in this case, since you have this I, this imaginary unit, these are oscillatory terms that in principle they do not vanish when you calculate them at the boundary. Now, without being too technical about the boundary term that we will simply neglect and we will not consider it, we will only consider the other term that we get by changing the sign of this integral and taking the derivative with respect to xk of x sub k here, so we get 1 from that. So we have dxk integral from minus infinity to plus infinity, and then we have e to the I 1/2 m over h bar x sub k plus 1 minus x sub k squared divided by delta t, e to the I 1/2 m over h bar x sub k minus x sub k minus 1 squared divided by delta t, like this. So you can see that we get basically this integral here multiplied by I h bar. And if we put these results together, what we get is the following. So maybe I can go back here, and we have found that this is equal to I times h bar times the integral dx e to the I s of x divided by h bar, like this. And this is just the partition function from this point y0 to this point x of t, if you want, which we have not used here, but you have to think that we have a starting point and an end point for the partition function. From this formula you can see that the average of the commutator, and inside this commutator here we put the operators x of t and p of t, is equal to I h bar, where the average of this commutator is simply equal to 1 over z, and then we integrate dx e to the I s of x divided by h bar, and then in here we have x of t, p of you have to pay attention to this. You have t minus here, and you have to think that this t minus will approach t, but from the left, because t minus is smaller than t. And then we have minus p of t plus x of t, where in this case p of t plus, where t plus is slightly greater than t but is approaching t. So this is how you should interpret this expression. And basically we have found something that we already knew from quantum mechanics, but now we have motivated it by means of the path integral formalism, and we have found that the path integral formalism, which is simply another way of rephrasing quantum mechanics in different terms, should contain all the information related to quantum mechanics. So it should as well contain these commutation relations. Before concluding, let me also clarify what we did earlier. One simple way of motivating the fact that we don't have boundary terms is the following. So basically when x of t is very large or very negative, so it's either equal to plus infinity or minus infinity, this is basically telling us that if we consider the trajectories here, well, if we assume that the time instant that we are analyzing is this one, we are saying that the trajectory that we are analyzing is one such trajectory where x of t is very far away from the two endpoints of our trajectory. It can also be in this other position here. So we are assuming that basically the complex exponential so far away is equal to 0. It makes sense because we should not get any contribution from points that are so far away. Those points do not contribute to our probabilities in general, so that's the intuition behind it. It would be easier to motivate it if you didn't have this factor I here, and you would have something like e to the minus s of x divided by h bar. In this case, the complex exponential becomes a real exponential, which decays very fast. But something analogous happens also if you consider such a function, or actually should happen if you consider such a function.